today's webinar one. I'm Michael Barker, University of Wyoming, and also the Director of Education for the Short Span Steel Bridge Alliance. I'm going to be talking about a plate girder study we're doing, and then Tanner is going to come from DeLong's and give us the overview of or a perspective from the fabricator. So here we go. And again, everybody, welcome. So here's what we're going to do today. I'm going to talk about economical plate girders for midspan bridges, and then Tanner's going to talk about specific bridges in Franklin County where Missouri really had an awakening of steel bridge production, and Tanner's going to give us a good talk on that, and then of course the Q&A. We're going to talk about these three things on the right, E-span, E-beam, and E-plate a little bit today because that's what I use to do the economical plate girder study. But a week from Thursday, we're actually going to go through them and find out what resources the Alliance has. And so again, this is me. We're going to talk about plate girders. So I'm going to talk about a study that we're kind of in the middle of. We've done some initial work. We're going to do some more work for looking at plate girders and W shapes in the 60 to 100 foot range. Okay, so right now, when we have a 60, 65, 70, 75, even up to like 90 foot, we start looking at W shapes first, and we might have those big W40 shapes that only one producer makes, or we're looking at heavy W36 shapes. And we kind of assume that the W shapes, since they're rolled and there's not a lot of fabrication that has to work on those to get them into a bridge form, that they're less expensive. But there's been several of us for years that have thought, no, we have some really good fabricators that can economically produce plate girders, even in those ranges. And the savings in weight is more than the additional cost for fabrication. So we're doing this study, and that E-span that I'm going to talk about a week from Thursday shows us that in that 60 to 100 foot range, we do want to consider both wide flange and plate girders, as you can see in that right picture there, that there is an overlap. And that's what this study is going to try to do, is say, hey, should we be considering both wide flange and plate girders when we're looking at a 65, 75, 85 foot bridge? And so why are we doing this? Here's a hypothetical example, and then I'll show you a more realistic example a little bit later. But here's a hypothetical example where that bridge on the right needs to be replaced. There's no doubt about it. So now the owner says, all right, I'm going to go out for bids. And that rolled shape turns out to be a W40 by 183, and it costs $590,000. And a pre-stressed concrete beams comes in at 570, and it becomes a concrete bridge, and it costs that owner $570,000. Very typical bridge bid result. But what if that engineer and the owner considered a plate girder? And because we have efficient plate girder production and economical plate girder designs, it comes in at 550. Okay, now it becomes a steel bridge for $550,000. Now we can argue whether it's a concrete or steel bridge, but this is saving that owner $20,000 because they considered both a W shape and a plate girder bridge solution here. And another reason I think this is important right now is that we understand that finding W shapes right now is pretty hard with the rolling schedules from our producers and the data centers eating up all of our steel. And so when we're looking at a 75-foot bridge, we should maybe consider plate girders. And that's what the study's about. Okay, so we have completed the initial part of the study where we looked at two cross sections from actual bridges. In fact, the bridges you're going to see are the ones that Tanner's going to talk about later. And taking those cross sections and then pretending I have a 70 foot, an 80 foot, and a 90 foot length bridge. Simple span. And now I need to find solutions for those for a W shape and for a plate girder. And that's where this E-beam and this E-plate come in, and that I'll talk about a week from Thursday, where these are optimized programs to do W shape and plate girder designs for simple spans that can save engineers hours and look at options, and it's so flexible. But that's the June 18th webinar, number 4. So we found these optimized solutions for these 3 cross sections, or these 3 lengths and these 2 different cross sections. And then we actually sent them to DeLong's, to Tanner, who's talking a little bit later. And he came back with prices and said, hey, if we got this as a bid, this is what we would price that out to in that moment in time. Okay, so that's a pretty good start, at least to see where we're at. So here we're going to look at those. And here's the first one, that's 70-foot simple span. It's the Lockhart Bridge section, which means 5 girders at 6 foot 2-inch spacing with a 2-foot overhang, and then a regular concrete composite deck. And on the top right, you just see part of that E-beam and that E-plate. It is an Excel program to give us optimized designs. And our optimized designs came according to what you see at the bottom. For the W shape, the lightest weight W shape was a W36 by 160. And for those 5 girders, it would be 28 tons. Plate girder, of course, one reason we like plate girders is that we can optimize the top flange and the bottom flange and the web thicknesses and all that kind of stuff, where those W shapes, when they get that big and heavy, are kind of thick. It is a symmetric, doubly symmetric plate girder, as the least weight at 22 tons with 16 by 3/4 top and bottom flanges and a 26 by ½ inch web. And it meets all the AASHTO and everything else. And we see here, here's the question. That plate girder uses 12,000 pounds less steel than that W36 by 160. Does saving that much weight save more money than the additional fabrication for the plate girder? Okay, so here's example number 1. Here's example number 2. I switched the cross section. Now I have only 4 girders up there. This is an 80-foot simple span. This is called the Hendricks Bridge. And now, since it's 80 foot, we start getting those mega shapes, the W40s and 44s, that are more applicable and can be lighter. In fact, it is here. The most economical W shape is a W40 by 167 at 26.7 tons. But we know that only one manufacturer produces W40s. And there's usually a premium on the price. So when we're considering W40, we should usually also look at W36, because those are made by multiples. Those are in the sweet spot of multiple producers. And we see the least weight 36 is a by 170, not much heavier. In fact, only 27.2 tons, ½ ton more. Okay. Now, when we go to the plate girder, we see that we can get down to 21.8 tons with a top flange and bottom flange of 14 by 3/4 and a web of 38 by 1/2. And this is that E-plate 140 that says this is the lightest plate girder you can produce that meets all the AASHTO requirements. So here's our 3 optimized designs for this 80-foot simple span bridge. And we see the plate girder needs 9,800 pounds less steel than that W40 and 10,800 pounds less than the 36 by 170. So there's example 2. Let's go to example 3. Then we'll start looking at these example results. Here's the 90-foot. Go back to that Lockhart, the 5 girders at 6'2". And for that W shape, the lightest is a W40 by 199 at 44.8 tons. The lightest, not W40 or 44, which means W36 or less, right, is 47.3 tons with a W36 by 210. And we don't know which one of those 2 is going to be less expensive, because there's usually a premium on the W40 compared to the W36. Then the plate girder comes in, and now we're getting a single symmetric shape that optimizes the construction design criteria and the strength and the serviceability and the service and those type of things with 15 by 3/4 top flange, 16 by 3/4 bottom, 38 by ½ inch web. And the plate girder, 25,000 pounds less than the 40 and 30,000 pounds less than the 36. And then the big question. Okay, we know that plate girders require more shop labor. Like the welding, it has to weld the top flange to the web. But they offer weight savings that we already saw. We saw the weight savings. But they also offer a couple other things. For instance, better fit up. That because the tolerances are tighter, putting in bearing stiffeners or shear stiffeners or even connection plate stiffeners can be easier or more efficient with plate girders. And of course, cambering. When we're talking about cambering a big W40 by 210, that's a tough job. Whereas for the plate girder, we can cut that into the web and make that a fabrication camber instead of cold or heat cambering. Okay, and of course, more refined detailing, we can save a lot of steel, which the question is, does that offset the additional fabrication costs? And so here's our table. You see the 70-foot on top two, or the top two rows, then the 380-foot with the W40, W36, and the plate girder, and then the 90-foot with the plate girder, the W40, and the W36. You see the tonnage there again. And then under that orange box are actual numbers from DeLong's. But because that's kind of proprietary and that type of thing, I did not want to show that. But we've got an answer for that coming up that you'll see. But there's actual numbers under that. And then that right column there says, here's what DeLong's, the difference in prices that DeLong's would quote if this was a bid project. And wow, what we thought would happen happened. Like for that 70-foot, the plate girder is the base cost. And if we went to that W36 and the additional 6 tons of steel, it would cost 9.5% more. Or if we go to the 80, that W40 would cost 10.6% more. And the W36, although it's heavier, 27.2 tons instead of 26.7 tons, is 4.6. And right there, you see that premium cost. That the W40 is lighter, but costs more than the W36 because there's only one producer that makes it. And they're going to charge a premium on that. And then the 90 is the same thing. We come in and we see the W40 is 25% more than the plate girder. W36, 23% more. And so this was really good news for us, we thought, because it gives another option to have competition to try to get the best price and the best product for our bridges in those ranges. Okay, so if we just look at this, of course, we can do some observations. Plate girder, less cost than W shapes. The fabrication costs are offset by the weight savings for these examples. And then that premium on the W40 makes W40 shapes less economical, less weight, but more cost than the W36. So those are some initial observations that we are keeping track of as we move forward on this study. And so if we went to that kind of hypothetical thing again, if a W36 bridge down there at the 90-foot costs 500,000 and concrete is 450, steel loses with only W shapes, and that bridge costs $450,000 for the owner. But if we take off 22.7% because we built a plate girder, that plate girder is going to come in at $390,000. And steel wins the bid with the plate girder, and the owner saves $60,000 by just considering whether we should look at a plate girder or not. So that's all good news, and we keep going. We're going to keep going. We're going to expand this study. Of course, we looked at 2 different cross sections and 3 different lengths. But there's a lot more variables that we want to consider. but we are going to we are developing a scope of work. We are going to do a bunch of optimized designs where we look at design comparison variables and then develop the optimized examples and then send it out for industry costs. And that's going to come from 3 fabricators. And when we do that, now we can average them so that it's not proprietary, that we're not giving away any trade secrets and that kind of thing. And DeLong's, of course, with Tanner on the line here about to talk, is going to participate from Missouri. And then High Steel Structures out of Pennsylvania, one of the larger fabricators out of Pennsylvania, is going to participate. And then Ohio Structures, out of Ohio, of course, is going to participate. And what we'll do is, of course, we'll look at them individually to see if there are any issues there. But then if we average them, then we can start showing some numbers. Okay, so that was my part of the talk. That this is something new coming out. And what we're hoping to do with this is, of course, to demonstrate the cost advantages that can be realized if we have optimized plate girder designs in that maybe 60 all the way up to 100-foot range. And so we're going to develop the examples that help fabricators and engineers and owners say, yes, I do want to consider plate girders when I'm at a 75-foot bridge. And of course, that's going to increase steel's competitiveness in bridge bids, but also hopefully save owners money. And then this all becomes part of our Short Span Steel Bridge Alliance education and marketing program, which you should look into on the website that will be shown a little bit later, I believe, or shortspansteelbridges.org. And with that, I'm going to turn it over to Tanner to talk about the people that put these plate girders together are efficient and economical fabricators. Tanner, take it away.
All right. Well, first off, thanks, Michael, for the introduction. And like I mentioned before, my name is Tanner. I'm a business development manager with DeLong's. I've been here for about 8 years and played various roles here. I had actually had a stint in sales before my current role, so that's why I was able to help with some of the pricing and some of the scope.
Hey Tanner, can you move a little bit towards your microphone? You're kind of breaking up a little bit.
Previously, and so Michael had talked about. Yeah. Can you hear me now? How's that?
Yes, that sounds better. Thank you.
Okay. Yeah. Michael had, like I was saying, Michael was hitting on kind of that 60 to 100-foot range for the spans of steel. And so here in Missouri, recently, we've had a lot of success on the less than 60-foot range, and that's kind of some of the examples I'm going to go over today. But the ultimate goal for today, really, kind of the theme between Dr. Barker's and I's presentation, is to be considering steel in areas that you may not have been before. And so I'm going to go into some examples of the Franklin County, what we're calling the Missouri version, and I'll hit on some other projects that we've had some success on steel as of late. So, and Michael, if you could give me control of the presentation, or just go to the next slide.
You should have it now. Try it. Yep, that's you.
Yep. All right. I'll go back one there. Okay. So problem statement. Go back one. There we go. Kind of what's led up to this. Back in 2017 and 2018, we had a downturn in the market for fabrication. So any fabricators on the call, you might remember, where it just wasn't the best years for fabrication. And so what that did was we actually had to take a step back into our business and look at, hey, why are we not getting as much steel in? What's the price of steel looking like? And so what we ultimately found was over the last 10 years, and I don't know, Michael, would you be able to go back one slide for me? It won't let me go back one for some reason. There we go. So what we found was in Missouri, many times steel was not even being considered. And we were talking to engineers, we were talking to Missouri DOT, and they were saying, well, you're way more expensive than concrete. You need to lessen your price, and that way you're more competitive. And so we said, well, where are you getting your pricing from? Where's all stemming from? And we did a little research into their EPG, the Engineering Policy Guide, and we found that they had some published pricing that you can kind of see in the slide there. And no matter how you cut it, they were saying that steel was 20 to 26% more expensive. And we were kind of drawn back from that a little bit, and we kind of had to, bust open the books a little further and kind of evaluate from a grassroots effort on how do we tackle this problem that we are having. Because in our gut, what we were finding was owners were paying more than they could for bridges. I mean, we've had examples where we were providing steel that was cost competitive with concrete, and we had unwarranted lack of competition. And that's not just from a steel versus concrete perspective. That's actually from a pre-stressed concrete supplier perspective as well. There's only about two predominant suppliers for the pre-stressed girders here in Missouri, whereas on any steel job, you have anywhere from 3 to 6 competitors bidding for that steel. So basic economy will tell you that the more competition you have, the better the prices are going to be from a supply and demand standpoint. And so we went to MoDOT. We said, hey, can you give us your Excel sheet for how you figured those numbers on the square foot price you see there? And they did some level of analysis. They looked at the last 10 years of data. They tried to compare, eliminate major river crossings, look at either 1 to 4 span bridges. And what we found was it still wasn't a true apples to apples comparison when trying to evaluate steel versus concrete. And so we took that Excel sheet, we made it more elaborate. We added a lot more filters within there. I kind of joke it was AI before AI was cool kind of deal, where we were able to then go in and filter out any jobs that were not what we call a typical. I'm going to use the word typical from the rest of the presentation. And what I mean by typical is kind of the bridges that Michael hit on earlier up to like a simple overpass bridge, anywhere from 2 or 4 spans. And so when we kind of evaluated for those filters and really got down into an apples to apples comparison, what we found was from the last 10 years of information. There we go, slide. What used to be a predominantly steel state has now only at 4% typical steel bridges. And kind of there you see where we have 15 plate girders, 1 wide flange. So not a large number of bridges to kind of compare to. And that was one of the things that we got feedback on was, well, your sample size isn't big enough to try to evaluate the economics of their product. Because what we found was we were actually a little cheaper, if not neck and neck with concrete. Well, our argument to that was, well, why don't you let more steel, and then we can also, increase the sample size and verify it. So what we did was convince MoDOT to kind of do a alternate letting, and we went and presented this to Learn and Earn workshops in Kansas City and St. Louis. We talked to consultants and contractors kind of about all the findings that we were having, and ultimately we published a white paper, which is coming up here now. And that's what you see to the right. And it basically summarized everything that we evaluated on and showed that, hey, we need to eliminate that pricing guidance that you have in your EPG because it's just not accurate. And also it's hard to keep up with, year over year. That was only a stint in time, whereas, as both materials, with the volatility of both materials, we want to make sure that the engineers and the owners are actually using accurate pricing mechanisms. So with the help of MoDOT and their staff, we were able to actually remove that cost guidance in December of 2018. And as they mentioned to us, they went ahead and they did a steel versus concrete alternate, which I'll hit on in a minute. But I also want to take a minute to just say any owners or any other states that are on the call, you might have similar mentalities or similar guidance in your documents that are not leading astray, but maybe providing some false guidance on pricing of the two materials. So just want to make sure, if you are a state or owner, evaluate that, make sure that it's still accurate, and also talk with your local fabricators on ways to maybe remove that or maybe put some more accurate proposals together. So So what happened when we competed the two? Well, we took a simple Scott County, Missouri job, 45-foot simple span, 26'8" wide. It was built in 2019. We even increased the length for hydraulic opening. So we added the length to avoid any scour concerns, and we increased the width for the number of lanes. This was a very rural road bridge. That's how the rest of the bridges are going to be for the rest of the presentation as well. But you see on the left, we have a composite rolled W shape, and on the right, a pre-stress I-beam. And so when these went to letting, we had 8 bids from general contractors, tied. Basically, we're when you're competing the two on an alternate, for those who are unfamiliar, that leaves the contractor to decide which material they want to use, whether they want to use the steel or the concrete side. And for this job, we got 4 for steel, 4 for concrete, and came back that galvanized steel was the winner for this alternate, and really saved the owner about $290,000. Not just a drop in the bucket or a neck and neck kind of competition. So we were pretty ecstatic about it. I think it opened some eyes here for the Missouri DOT, especially for the owner as well. And so with that kind of momentum going, Missouri has a lot of design build programs going on right now. There's anyone that's trying to drive through Missouri right now knows we're trying to widen I-70. But on the back end, they do a lot of bridge bundling projects as well. And so one of the first larger ones they had was called FARM, Fixing Access to Rural Missouri. The goal was 31 bridges for $26 million. And basically, it's a set price, variable scope, really who kind of provides the most bridges to be replaced, really wins the award for the project. And then the winning contractor on this one was Lehman, who partnered with Wilson and Company. And we were able to supply 25 steel bridges, and they utilized, for those unfamiliar, the simple for dead, continuous for live design. This project also just won an AIC Prize Bridge Award in the short span category, and I think we're going to be featured in one of the steel construction magazines here in the coming months. But there's a lot more information on that site about this program in general, a lot more photos than are provided here. But these are simple bridges. I mean, just your straight up workhorse bridges. A lot of the spans were under the 50-foot range, galvanized steel within blocks. And that's why we were able to provide 25 of the 31 bridges here. And 3 of the other ones were actually box culverts, so not even a pre-stress option. And so with them being able to supply so many bridges, they got some bonus points on number of bridges that were awarded there. So they got the 1.5 points bonus. Quality and longevity with the galvanized beams. As people know, we have a 100-year expectant in these rural settings that we are. Kind of seeing the picture here. This is a very low water volume creek that may flood once in 100 years. And so the galvanized is a pretty good option for here. And another big thing is full depth cast in place deck. It's an issue that Missouri is fighting right now with the use of pre-stress concrete panels as the filler between beams. It doesn't provide a full depth deck. And so these steel options here allow for that 8 or 8.5 inch deck. And you can assume that you won't have to touch this bridge for another 100 years. And then completion and maintenance of traffic. They scored second highest on this. And that was because of the lighter bridge, lighter equipment to be able to set it. I know a colleague of mine and myself went out and watched them erect the bridges. In a matter of a morning, with the use of a telehandler or a really, really small crane, they're able to take these beams off our truck, set them up in place, and go on their way. I mean, the average time frame for closure, I think, for these bridges from tear down to building new was about 4 to 5 weeks. And you want to talk about a rural setting. I mean, there's a lot of tractors, a lot of combines going over these. So kind of limiting the effect on the farmers, the local communities for these low volume roads. And so with their pace of construction, they were able to maximize that in their points scoring. So yeah, kind of hit on the economy of steel bridges, the performance of steel bridges with the galvanized steel, and the equipment and ease of construction. And really what led Lehman as the successing team, and it was the only one that actually chose primarily steel. The other two teams chose primarily pre-stressed concrete, and you can kind of see where the scores came out. Again, close and neck. Again, why we need to be considering both options. But that was a very successful bridge bundle for our Missouri, for DeLong's, for steel in general, and it led into some other bridge bundling successes I'll hit on here in a minute as well. So then continuing that momentum, there was an engineer in Franklin County, which is kind of the basis of our whole presentation today, who said, well, it seemed like these alternates kind of led to where both materials had the best pricing. And so this engineer said, I have a string of small bridges like this coming up and in my county, and I'm going to let all 5 as an alternate and kind of see where the chips lie. I mean, what contractors prefer, where does pricing come in at for both materials, and really just kind of do an apples to apples comparison between the two, steel and pre-stressed concrete. So you can see there, Michael kind of hit on the Hendricks Road, which is what we'll hit on more in a minute, and then the Lockhart Road too. But one thing I want to point out is just how, one, that steel won 4 out of the 5 alternates, but also the order of the bids. I mean, there are some bridges where you only had 3 bids, some bridges you had 8 bids, and the order of them. So some you had steel, win first, second place. Some you had concrete win first, second place. So the moral of the story is to be considering both materials, and really for us at this time frame was steel was really just rocking and rolling in Missouri. Contractors were getting a lot more familiar with the material since over the last 20 years prior, they were warranting or lacking the competition that was going on. So fortunately for DeLong's, we were able to supply 2 of those 4 steel bridges, and overall cost savings for steel saved the owner about $282,000. So you put that back into the program, that almost gets you another half a bridge that they can replace just off the material selection that they used. So we're going to take a closer look at the Hendricks Road and the Lockhart Road Bridge. I know Michael and Dan and a colleague of mine went out and took some pictures, so you actually see them in some of the pictures here. But yeah, looking at the Hendricks Road, 45-foot simple span, 24-foot roadway, 21 by 101 girders, weathering steel, which was the most economic for these here. No skew, integral abutments, channel diaphragms, just your simple workhorse bridges out in rural Missouri. And here's some pictures from the field. There's Michael and Dan down in there underneath there, just probably nerding out over the steel. And you can see kind of from the pictures, we got SIP decking there, simple overhangs, integral abutments there. Nothing fancy about these bridges, just straight up workhorse bridges. And you can kind of see the setting we're in here, rural Missouri here, widening it to 2 lanes when we did it. It was a 1-lane bridge before. So able to help the local community as well as giving the owner a price competitive option. Now we're going to go into Lockhart Road. Really simple, similar bridge to the Hendricks Road, 41-foot, 6-inch span, 28-foot roadway, W18 girders, again, weathering steel. This one actually had a 20-degree skew. And the other economical part about this I'll hit on in some of the pictures is it actually had bolted diaphragms. I know AASHTO has been hit or miss on allowing this as of late, but was a design that for the fabrication side of things is very, very economical. And I'll kind of show you when we get to that part. But yeah, simple bridge railing as well. Again, this ain't an interstate or anything. It's just carrying 2-lane traffic, a few hundred cars a day. Here's some of the pictures from the side, underneath. Some simple wing wall abutments there, integral abutments there. And here's that bolted I was telling you about. So from a fabrication standpoint, with these rolled beams being as short as they are, and with them having no welding involved, they really go through one piece of equipment and with no paint or anything on them are basically fabricated. So we are able to really automate this process. We have automated equipment to do the angles. We have automated equipment to do the channels. So there's really doesn't get much more economical from a fabricator standpoint on this Lockhart Road Bridge with all the simple details, all the bolted details. And again, you can kind of see we're in rural Missouri still. I mean, there's even hay bales in the background to kind of give you a concept of where we're at here. But very simple, straightforward bridges, and all bridges that you can design using those tools that Michael hit on earlier. So then once we had the success with farm, we had the success with the Franklin County bridges, we said, okay, well, what's MoDOT's stance been over the last 5 years, 2021 and 2025? So you kind of see there where, things are kind of trending in the right direction. This was still those typical bridges I talked about earlier, plus 50% in the steel count, negative 39% in the concrete count. Love to see that. I'm sure a lot of people on this call love to see that. And so what boils down to is we went from a 4% steel state to a 10% steel state, all in the matter of about 8 years. And so those numbers there I also want to add is not including the design build that I hit on earlier. So I already mentioned the farm project. Immediately following farm, there was another bridge bundling project called the Northwest Bridge Bundle. We were able to provide 24 steel bridges for that bundle as well, almost identical to the farm package. And again, that was 24 out of 31 or 32 bridges, so predominantly steel, a couple pre-stressed concrete. Then we went down to Southwest Missouri, where we had the I-44 improvement project. They're actually just let out another I-44 improvement project near St. Louis. But down in Southwest Missouri, 12 of 20-something bridges was steel as well. And something interesting with that bundle was there even was some 3-coat paint applied to the steel over the I-44 interstate, and still came out competitive against pre-stressed concrete. Shortly after that, we got into the casing or basin, where we had 4 steel bridges there, a lot smaller of a bundle. I think there's about 13 total bridges getting replaced on that bundle. And then just recently, we got awarded 5 widenings and 2 new bridges on the Improve I-70 Roachport to Columbia project. So steel kind of going everywhere in Missouri. We love to see it. I know this SDCL design is really kind of hitting home and becoming a lot more popular. And we've been fortunate to be able to be the fabricator on a lot of that. And so kind of wrapping up, summary and conclusions, kind of how I said the goal for today was just the competition between the two materials is healthy. It's healthy for cost. You kind of see where in the Franklin County, Missouri, where we had the 4 out of 5 bridges were chosen steel, but that one was concrete, and it came out cheaper. The quality of bridges, and what I mean by that is just making sure that the bridge serves the purpose in its place, and making sure that, with steel, galvanized steel, we know that the maintenance is really low. So even if you have to pay a little bit more up front, or a lot of times it's even still cheaper than pre-stress, you don't have to be touching the bridge again for another 100 years. Industry responsiveness and capabilities. What this is really referring to is when you are continually supplying the material for the state, you keep that competition alive and well. And so what we found over the last 20 years was, from the contractor standpoint, they were getting a little more unfamiliar with steel and a little more familiar with pre-stress. And I think that's why the Simple for Dead, Continuous for Live really hit home in Missouri, because this really was the steel version of a pre-stressed concrete bridge. You're setting simple span steel, you're pouring a diaphragm, you're pouring a deck up top. And so that's where, from the contractor standpoint, they could keep the methodology the same, which is a lot lighter crane equipment, a little different decking material, and provide a full deck for the state. And steel and concrete are competitive on first cost and life cycle cost. I know back in 2020, HDR did a huge life cycle study between steel and concrete, and found that the two materials should be kind of intertwined and considered for all projects. And steel or concrete may be the lowest cost for a particular project. You kind of, again, saw from Franklin County where, for whatever reason, that one bridge pre-stress was the chosen material. And so really, owners, designers, contractors, everybody on the call, my advice to you is to consider both materials, use the tools that Michael had talked about and will be talking about here in a couple weeks on the next webinar, using E-beam, E-span, E-plate 140, getting a preliminary design, and talking to your local fabricator. I know that we help out Missouri DOT quite a bit as far as looking at preliminary designs for budget pricing and kind of making things more efficient. So you start talking about what Michael talked about the plate girder versus rolled beam. Getting a local fabricator involved is the best way to kind of get a feel for where the market is currently. Because we do switch. I mean, there are times where rolled beams are going to be cheaper than plate girders, or the vice versa. And really, at the end of the day, I mean, as long as we're using steel, DeLong's is happy, the industry is happy. But getting your fabricator involved and kind of getting their insight on they have their finger on the pulse much more than what owners probably do. And so reaching out for them, getting some insight, getting some help, and making sure that the material chosen is what's best for not just the owner, but for the taxpayers for your local municipalities.